Hi, my name is Micah Flack, and today we will be talking about my research topic, PRINTSHOP, assessing operating systems and capabilities of serial print devices. So to start off, introduction. So the Federal Trade Commission, every year they put out reports for fraud, identity theft, and miscellaneous report cases. In 2012, there were 38,000 roughly reports of credit fraud, and in 2022 there were 87,000. So there's roughly a 30.5% increase over that decade for credit card related fraud. And between the years 2020 and 2022 alone, there was an increase of 14.6. And that's out of a total of 5.1 million cases in 2022. So the prevalence of financial cybercrime has been increasing year over year, decade over decade. And I mean, it's kind of expected as the payment models that we use for things shifts. And that's especially so for like retail cases, because before you need purely cash-based or paper credit systems. And now, I mean, you have digital payment systems like Sure, POS systems, or Swipe. But, a key part of that process and the reason for this research topic is that securing that entire process from the endpoint or the point of sale system to the payment processors, is critical to reducing these fraud cases. And we picked the serial print devices just within the financial sector as sort of an example of this. These devices are used for many cases just because it's a cheap and portable option for printing, either for receipts or reports. So it's not just point of sale systems in a retail setting or environment, but it's also ICS or HMI systems that also use these devices. It's just from a point of framing the perspective, the financial case makes the most sense. And this is an example of the point of sale systems that have a accessory serial print device. On the right, it's a little internal to the case, so it's kind of harder to see. But on the left example, we have the device with the paper roll coming out of it. That's the type of device that we'll be targeting, or if that's used for this research. So some related works real quick. We have WooKey USB devices strike back. This was an example I used just because in their paper they discuss not really attacking systems, but which different real-time operating systems or embedded systems are the best for creating a secure USB device. That paper was particularly interesting just because that'll be a key component as a part of the survey of this research, and then for future research after this, creating a design artifact that'll be based off of the survey data here. So we include that paper because we want to look at the different operating systems they surveyed, which software protections they had, any hardware protections that they could work with, like for memory or trusted enclaves. And then for the Baheti JY paper, real-time operating system security, that just covers some of the basic security protections offered by real-time operating systems and some of the shortcomings they have. In particular, one of the main concerns with real-time operating systems is the fact that the tasks are scheduler-based, and you can't really add agents or any sort of monitoring to those systems without impacting the performance, which is key because typically these systems you can't have any downtime. Otherwise, you get issues with reporting or interrupts with other parts of the process. And then third paper, we have Y He Zizo, and it's rapid patch firmware hot patching for real-time embedded devices. This paper was included because they proposed and designed a system for hot patching real-time embedded systems, so specifically operating systems like FreeRTOS or just the original RTOS. And through their tool, they're able to, while the device is running, or the system, they can push firmware patches, either like specific memory regions, to the device in memory while it's still running without having to shut it off. How this relates to the actual research topic? Well, it might be a method that could be applied towards later pushing the modified firmware onto the devices that we're looking at. And then you have JTN et al. SOC plug and pray today, understanding USB insecurity in versions 1 through C. And this one just kind of describes the USB standard, some of the protections it has, and then also the requirements for creating HID cloning or HID hub devices, and also some of the different attacks that can be played at each of the layers. So you have like human, application, physical, and then just, each of the attacks that you can do. So like with physical, you have signal eavesdropping or signal injecting, and with the application layer, you have other things like HID cloning or duping. So for proposed research objectives, the goal of this research is to understand some of the hardware and software capabilities of serial print devices. So what's the hardware that these devices use? What firmware is it running? What type of bootloader is it using? Is the device running like really minimal hardware that supports just the base functionality and just that, or is it running like a Cortex M4 with a lot of room for overhead where you could add agents or HID functionalities that maintain like the original print functions, but also those for creating like a bad USB-like device. So, and then we'll get into the research questions, which are going to be a little more specific. So the 5 questions that we're looking at here: what is the baseline or minimum hardware the devices are running? What software is being used? OS, libraries in particular, because sometimes if later on for design artifact or future research, which is what this proposal is aiming to support or justify later, is, using the libraries, if we can identify known vulnerable ones in memory, can we then use those as a method of deployment for whatever modified firmware we create? So yeah, and as an example, I think you do touch on this later, but there's like the Trek HTTP library, which if the device is running a web server, which some of these are because they do have networking capabilities, you could use that vulnerable HTTP library to push the modified firmware in memory. So the third question, can the software firmware be modified? So closed source is the operating system? Are the libraries that it's using closed source or proprietary? Can we push a open source OS onto it like FreeRTOS or Recon OS, which is a version of RTOS but with threading? So that's one of the questions. And then if so, how much can be modified in memory? So when we get to the teardown process of the research, is there anything that can be modified? Are there hardware protections against reading or writing to the device? And then the 5th question, assuming it's possible, can we estimate how much of the original functions can be maintained and whether or not there's any functionality for creating a HID clone, which would be the bad USB-like device? And then all these questions should be answered through the survey data, and that's going to be described in the methodology process gathering data sheets, technical specs, and some of the firmware analysis. So for the methodology, we've got several parts. We need to identify the sample populations, so most popular and available printers, technical specification, and datasheet gathering. So we'll pull information regarding hardware capabilities and I/O. And then there's the hardware teardown and documentation phase. So we're going to take photos throughout the process, identify hardware components, and then using the serial numbers for the components, identify the manufacturer, the component, and then gather more information like the datasheet. In this example, we have for SNBC BTP S80 thermal printer, which we'll show an example of later. It has a ARM Cortex M4 SoC. It's the main chip, and it's from NXP, the LPC 4078 FET 208. So that's one example that we'll go through that and pull the necessary information because it aids the recovery later. And it'll also inform us of some of the hardware protections. And then the last phase, using debug tools, we'll gather firmware and bootloader information. And this is all the information that we're hoping to survey. So the methodology approach, it's quantitative. We'll use cross-sectional surveys, and a small sample of population specifications. So, it's single printer device and the data sheets for the device and each of its key components. And the reason that we chose all this, or this approach and this research tool, is because it's best for gathering and comparing data across multiple samples or a small population, and then comparing them in real time or as they are now, and not something that's surveyed over a long period of time. Because we are conducting all this research within the semester. So an example of the surveyed device specifications. So this would be for the SNBC BTP S80 thermal printer. And in this example, not all of this is necessarily needed, like the max print speed for, the later design artifact research that this aims to support. But it just kind of helps draw some parallels across the devices. So we have things like max print speed, printing method, paper roll type, barcode support, printer interpreter. And the barcode support and printer interpreter especially are useful because they might hint at some of the supporting libraries they use, like the ESC POS. That's how commands are delivered to the device and the expected formats and data it should receive. And then we have an idea of some of the supported operating systems, development kits, the data buffer, so that should hint at some of the physical components or the hardware that the device is using. And then we have power supply, current power usage, and safety or EMI specifications. So the next example, so this would be survey data from the SoC for the device or the main chip. This example is with a Stellaris wire SoC, so it's not the NXP chip that we mentioned earlier, but just an example of some of the things that we're looking at. We have architecture, platform, frequency, memory, firmware, advanced communication interfaces. So these could be things used for like side channel attacks or debug interfaces, which is what we'll mainly be using for the hardware surveying. And then the package format, which is important because that'll tell us whether or not we can even, not even how much, but what interfaces or what sort of format we need used to be able to interact with the chip. And then for this table, it's an example of survey data for memory chip. So here, just an example of what we're gathering. We have the power delivery needed, so it's 2.7, 3.6 volts, and then things like the software features, memory architecture, programming, erase commands that are supported, because that might be needed if you're looking to reflash the memory chip. And then also some of the protections it has, which in this instance is really important because, as you can see, it mentions that there are hardware protections for limiting the access to regions of memory on the chip. And then also the package format, which is needed for some devices. You need to specify the configuration that's used when reading or reprogramming them. And then here, this is an example in the hardware assessment portion of the proposal. So when we identify a chip and the manufacturer, this is Texas Instrument. The serial number is LMS or LM3S2798, I think. So using that information, we got a data sheet. On the right side of the figure, you can see the processor data sheet, and it explains the pin layout. So starting in the dot here in the top left of the chip, that indicates where to start counting. Looking at the data sheets in a counterclockwise fashion, and that tells us what pins we need to use to access the debug ports for the device. So this is the method that we'll be using for accessing some of the firmware memory analysis portion of the research, and just how we'll go about gathering and establishing that information. And then here's an example of a serial printer type device that we've mentioned a couple of times. It's a thermal printer from SNBC. It's the BTP-S80. And on the right, we have some of the ports and connectivity that the device has. So it has a RS-232C serial connector, has Ethernet, and then it's also serial USB. And depending on which model of the device you get, there's an expansion card that can allow Wi-Fi and Bluetooth networking. So here we have the research timeline. In the paper, it's research lifecycle, but this just kind of breaks up the start date, end date, and the expected time for each stage of the research and the expected timeline for the final research paper to be finished. So we have review, surveying, disassembly, and writing. So for reviewing, we're just reviewing the research process or proposal that we've just described and refamiliarizing with it so that we can make sure that the objectives are aligned for the actual research. And then we have surveying, which is just gathering the necessary technical data for the devices, acquiring them also if we haven't already, and also just all the data sheets that we'll need. And then we have the disassembly, which is tearing down the devices, identifying components, documenting, taking pictures, and then writing, which is just collecting everything, preparing it, and writing the final formal report. And then finally, we just have our conclusion. So as the financial cybercrime is growing, it's important that those systems are secured. And although point-of-sale systems are not necessarily the usual or a key component of those crimes, in some cases it's not even the POS system itself, but the card skimmers are attached to one of the accessory scanner devices, which doesn't actually interact with the POS at all. It's just sort of manning in the middle signals as they're collected. So that is different from how this research is approaching it, but I still believe that the research is justified in the sense that it's exploring the entire environment in areas that have been researched before, which is the serial devices that are connected to it. So using the data that's surveyed then, we're going to determine some of the hardware and software protections of those devices, their capabilities of the hardware and the firmware, and then using that information with a little bit of firmware analysis, determine whether or not we can create a modified version of the OS with bad USB-like capabilities later on as a future design artifact research. So that's everything. This is my research proposal. If you have any questions, feel free to drop them into the thread on D2L. Otherwise, that's everything, and thank you for listening. Bye-bye.